A modern digital logic course needs to have associated with it some type of hardware description language. And for this course, we're going to use Verilog. So one of the things I wanted to talk about at the beginning, before we get deep into the details of Verilog, is that Verilog is different than regular coding, and you need to approach this with the right mindset that what we're trying to do here is simulate circuit behavior. Not only simulate circuit behavior, it turns out that we can write Verilog code to actually design circuits. So that's pretty far down the road, but let's talk about the differences between Verilog and traditional software. Okay, so for the first thing, let's talk about what you already know. What you know is that software runs in a sequence when you write regular code. If you had A equal B and then followed that with the line B is equal to A, one thing happens first, then a single thread walks down the page, and then the next thing happens. With circuits, circuits are laid out all at one time. It's a physical circuit. There's a different thread that happens. Things happen in parallel. So let's talk about this. In code, if you wanted to come up with something that swapped two signal lines, okay, or signal variables, this is what it would look like. So don't worry about the supporting structure here. Focus mainly on this particular sequence of commands where B is assigned to A and then A is assigned to B, all right? Normally, if you make assignments like this from top to bottom, this would look familiar and you'd be tempted to think of the sequential nature of code. So predict it. If you did this, if you said B gets assigned A and then A gets assigned B, what would happen after one clock tick? What are the values of A and B? Well, with regular traditional software, you would think, okay, B is equal to 0, so A is going to get assigned to 0. And then, now that A is equal to 0, B is going to get assigned to 0 as well. Okay, so that's what you would think would happen when you use traditional software writing techniques. However, it turns out what happens in Verilog is these things would just switch values, that swap. All right, and the reason for that is things happen at the same time. If we circle back, if these things happen concurrently on a clock tick, all right, then at the same time that A gets loaded with B, so B is a 0, A would then be a 0, A gets loaded into B, but A is a 1, so B would be then a 1. So these happen simultaneously, and this is truly just a swap. All right, so this is one aspect that matters, all right, whenever you start thinking about describing circuits in Verilog. So I like to always emphasize that circuits are physical, everything happens at once. We write software to simulate the operation of circuits. Because it's software, it forces us into this sequence. We have to write sequences of code, right? Because we have editors, and that's just how you put things into a computer. There's no choice on that. But if you think about it differently, it becomes a little more obvious on what you should do as we get deeper and deeper into Verilog. Okay, the other thing about Verilog is that unlike regular software, there's not really a print statement. Okay, so in regular software, you can print things and see what happens. But in this case, you have hardware that you're simulating. So there's a division naturally that shows up in Verilog. You write software to simulate the operation of hardware. But then you have to run the hardware. You have to initiate the signal changes that make things happen within the hardware. So there's two different things that show up in your Verilog source files. This is also a different concept from what you're used to. When you write code normally, you can debug it with a debugger, or you can inspect variables at certain points with breakpoints. But with a circuit, it's always happening. So it's more like you're investigating what signals look like instead of just variables. And that's a different mindset. Okay, so I also want you to know that Verilog is just one one choice. We happen to choose this because I think it's the easiest to learn, and also it's probably the most prevalent uh, in industry. Actually, SystemVerilog might be more prevalent, but I would say Verilog, the difference is that SystemVerilog implements Verilog, but in ways that hide some of the underlying mechanisms. And so that's why we like to teach digital logic with Verilog instead of SystemVerilog, so that you learn the details. And then as you get better and better with hardware design, you can switch over to SystemVerilog, which is a little more efficient in many ways, common in industry. Okay, there's another classic, VHDL. It's long-standing history with this. This came out of the Department of Defense, and so there's still some industry people that use VHDL. All right, next, the payoff. It turns out that in the old days with digital logic, all right, when we learned about how logic circuits worked, we would go into the lab and we'd wire up really simple circuits. Because we were wiring them up, it was pretty tedious to make anything that wasn't just basically, a very basic kind of circuit. So because we have software descriptions, we can actually implement pretty sophisticated designs on FPGA boards. So think of an FPGA board as a way to represent hardware that's programmed in a way where I can implement any circuit that I wanted to within a digital logic class. Okay, so that's the thing I wanted to talk about first, to just sort of prime you to understand that there's differences, and there's also similarities, and so that's why it's kind of a challenge to start with Verilog. There's no simple print statement. We're going to get into these things in a little more detail. It's a longer workflow in general. You have to simulate and synthesize before you actually generate hardware. There's levels of abstraction that you have to master. These things we'll be talking about in the course.